Oh, I'm ready whenever.
Okay. Go ahead.
Good morning, everyone. Welcome back to Plant Science. I'm still in the process of grading your all's quizzes from the ecology thing, but I just wanted to say, whenever you're getting the automatic, response from the quizzes, just know that I do go through and manually grade those too. So Canvas sometimes messes up, and or I'm probably mess Canvas up. Either way, just wait until after I go through that. Don't take your score at face value. Usually we'll give a curve too, because I think to me that means that I messed something up. So, all right. Well, we'll get into the next chapter. We're talking about climate and weather and how that affects plants and crop development. So right now, we're getting ready to transition into autumn. Everybody knows what tomorrow is, right? The equinox, the autumnal equinox. So we're starting fall officially tomorrow. Even though it might feel like fall has already started with the cooler temperatures, it's just officially starting tomorrow. All right, well, let's get into this presentation. All right, so talking about climate. And I think one of the most important things to start off with there when we're talking about climate is just the definition of climate, and noting that it is defined as the prevailing weather conditions of an area. Very different from weather. Weather and climate are two totally different things. Weather is part of climate, but climate is kind of looking at the long-term weather conditions over a large area, whereas weather is the actual values of those climatic variables in a very short period of time in an event versus over a long period. So we usually think of climate as being a function of temperature and moisture mostly. So temperature due to how much sunlight we're getting and the intensity of that solar radiation. Moisture, of course, mostly from precipitation, but also kind of a function as how wind affects precipitation and how quickly it is evaporated. So climate, we look at these two kind of main factors, temperature and moisture, and how they vary according to the season over a large area. So we think of climate being fairly stable over a large area, and think of where we are in Virginia, kind of based on the latitude. So we're in the mid-Atlantic region, and due to that, we have a very similar climate. We need to know both the climatic details as well, as the weather. I think for us in the production of plants and animals in agriculture, we need to know a lot about both, because the climate is really kind of saying what we can produce given the kind of broad spectrum parameters, whereas the weather kind of modifies that to a certain extent. So it's really all kind of governed by how much solar radiation that we get, which is primarily determined by the latitude, but then also modified by the altitude, your elevation, as well as just by the time of the year, the season. So we look at climate kind of in two, views, two perspectives. We look at it as the large scale, the macro climate. And that's saying for us that we're in the mid-Atlantic, and within the mid-Atlantic region, we're probably going to get a certain range of temperature and a certain amount of moisture, depending on kind of where the trade winds, where that wind is pulling or taking moisture as well. So climate is mostly modified by, on the macro scale, by the large scale features. So the land masses themselves, things like mountain ranges, large bodies of water like oceans or seas, the Great Lakes would count there. Those are all kind of macro climate features. And we can't really do anything to change the macro climate. The microclimate, on the other hand, is the kind of similar idea, moisture and temperature, but looking at it in kind of more on the farm level. So we get similar effects from the microclimate, and it can also determine what crops we can grow. If we can really look at governing the microclimate, kind of affecting it in a small area through things like thermal mass, whether that is like a stone building or a rock wall, or even just soil can be thermal mass. Smaller bodies of water like ponds could be thermal mass, and can also reflect light. So those are things that kind of change the microclimate, what you actually see in your site. So it's important to look at both. We think of like hardiness zone kind of more as like determined by the macro climate, whereas you could grow things outside of your hardiness zone if you have a certain type of microclimate. So USDA defines the hardiness zone. We'll talk about that a little later. But for us in Southwest Virginia, it's 6B. I think it varies for you guys. You have to figure that out looking at the map, but I think probably most of you are in like a 7, maybe a 7B, and that's kind of more of a macro climate kind of issue. But how you might be able to change things on your own scale on the farm can affect the microclimate. So for instance, one of the things that we do with like fruit trees is we might plant them, say, on a south-facing slope because it warms up. That's a different, it warms up quicker and it stays warmer longer. That's like a little microclimatic feature. I think of the microclimate as, trying to get some knowledge of your site and how the site affects the weather, basically, in your little area. So things like a ground depression, a low-lying cool air sink can affect your microclimate. So we think of climate as the kinds of natural vegetation that grow in an area. But we also have to note that vegetation can also affect the climate. And I think vegetation is more effective on the microclimate scale, although large areas of forest can somewhat change the macroclimate to a degree, a small degree, but it can change it slightly. So anyway, think of both macroclimate and microclimate and climate and weather on the scales. And I think that we have to be in some ways aware of the climate, but very much so meteorologists if we're going to be producing any kind of crop, whether it's plant or animal. It's also important to note that our activities modify both macro and microclimate on a small or large scale. So if you think about urban areas, there's this whole issue and a body of research going around the urban heat island effect. You got a lot of asphalt that's absorbing its thermal mass, absorbing a lot of that heat and making it warmer for a longer period of time. So if you go to, say, Phoenix, Arizona, which of course is already a very hot place, but it's so huge in terms of urban sprawl that it's very affected by the heat island issue. So if you go to an area, at the same elevation just outside of Phoenix, then it'll be cooler than somewhere in the middle of the metropolitan area. Another issue that humans can affect climate is through deforestation, and forests tend to have kind of a modulating effect on the climate in terms of storing moisture for longer periods of time. So you clear forests, then it can lead to a drier climate, both on the large scale as well as the small scale. Also, we can affect precipitation and light intensity due to dust, other pollutants. The issues, of course, out west with forest fires taking place. I mean, I know some of those were probably naturally started by lightning strikes, but some of those were also inadvertently started by people. And so we're generating pollutants in the fact that we're burning trees, and that can also have an effect more on the weather, kind of short term, but it can affect long term the climate to a certain degree. Again, not a huge effect, but it can affect it. All right. So looking at climate and how plants deal with that, the wild plants kind of evolve in place through the survival of the fittest to grow optimally in the climatic conditions of their natural habitats. And of course, it's the same deal with the crops, except we've spread them out and we've kind of put evolution on a faster time scale, if you will. And that's changed the way that they grow optimally. We've modified the climatic conditions, modified the habitats. But generally, we think of a plant is able to grow in a place where it adapted to whatever climate it is, certain amounts of moisture and temperature. And if it goes out of that range, then the plant health declines. We think of these adaptations kind of amongst species of plants, little variations within the plant as different ecotypes. So, say a blueberry, a wild blueberry on Mount Rogers here in Southwest Virginia might have more adaptation for cold than a wild blueberry of the same species in Georgia. We have those same adaptations also occurring in our cultivated plants, except that we are playing a part in that selection. It's natural selection plus human selection, and we're kind of exploiting some of these natural variations probably to a higher degree to allow plants to be grown outside of their center of origin. So as I mentioned earlier, all of our climatic factors are primarily determined by sunlight, solar radiation. It's the major energy input for our planet, it really drives Earth. And it's important to think of sunlight not just as light, but also as electromagnetic radiation. And we govern that radiation by wavelength. So wavelength here is measured in nanometers, and that's looking at this electromagnetic energy coming from the sun being radiated towards us, towards our planet. And it occurs on a spectrum, and about 40% of that light spectrum, kind of a thinner band of it, occurs between this particular range of 400 to 700 nanometers of wavelength, and that supports the plant's actual photosynthesis. That's what they perceive, and and how they're able to grow through this kind of thinner section of light coming out of this magnetic spectrum. So kind of looking at that in terms of in a graphical representation here. Radiation is radiation. It's electromagnetic as it's coming from the sun. So we have short wave radiation, long wave radiation on this end, with things like radio waves, microwaves, a little smaller, infrared light, which we can't see, but we feel. And then we have our visible light spectrum. So you can see that the length of the waves is getting shorter when we get to the visible light. And that visible light spectrum, think of it as that image of light passing through the prism. And we have white light, which appears to us as, kind of white anyway. But if you pass it through a prism, then you see that it gets the colors of the rainbow, right? The Roy G. Biv, the red, orange, yellow, green, blue, indigo, and violet. And then beyond that, we have ultraviolet waves, X-rays, gamma rays. These are all coming, basically, it's energy coming from the sun. They're all floating around, but the visible light spectrum is what we see, and what is important for plants as well. So you can see here how chlorophyll and the different carotenoids have basically are affected by that visual light spectrum. They respond to red, orange, and yellow over here, as well as blue, indigo, and violet. And they say that blue, indigo, and violet are kind of more for our vegetative cycle of plants, where they're just growing new leaves, new stems. You see more of the response on the red, orange, yellow spectrum for the flowering of plants. And really, they have to have both, but in a different times, different life cycles. They have a different response to the different spectrums of light. Note that they really don't have any response to green light, and that's why plants appear green to us, because they're reflecting that spectrum of light. They're not absorbing it, they're reflecting it. So it's very important to look at the solar radiation from the perspective of that's what governs our climate, and it's also what governs the growth of plants and photosynthesis. And there's kind of a confluence of the energy of both in many ways. All right, so how does it affect us seasonally? First, we look at that solar radiation and its intensity as being the highest, of course, at the equator, at 0 degrees latitude. But that intensity decreases at both higher latitudes and lower latitudes as we move away from the equator, closer to the poles. The angle of approach also decreases, so that sunlight is not as intense, and it's also spread over a wider surface area, which makes that intensity even less. So the solar energy reaches the Earth's surface. The solar radiation passes through, depending on what our angle is, towards the sun, which changes throughout the seasons. We also have, of course, weather affecting that solar radiation in terms of clouds. So cloud cover can absorb a high proportion of that incoming radiation, and then it can kind of modify or attenuate those differences in the different latitudes, which also is going to change through the season with our tilt towards the Earth. The tilt of the Earth on its axis towards the sun. Because the Earth is revolving going around the sun, one trip around the sun each year, but we're revolving on our axis completely every 24 hours. That gives an average day length throughout the world of 12 hours. And it's like that all the time at the equator. But because the day length is going to change at different latitudes, moving away from the equator, because of the way that the Earth is tilted on its axis at 23.5 degrees, which is unique to our planet. No other planet in this solar system has this degree of tilt. And because of that, they have either like Venus has a much higher degree of tilt, and it doesn't really change as much in terms of how it's tilted towards the Earth, or how it's not revolving quite as much as the Earth. So with Venus, it doesn't have much of a change in seasons. Uranus, on the other hand, has a lower degree of tilt, so it's having really wild changes in the seasonal variation. So variations in the day length also add to that effect of the variation in light intensity with the latitude. So it's how we're tilted either towards or away from the sun that governs the seasons. So at equinox, we're actually not tilted relative to the sun. We're kind of even on the axis. So the day length is around 12 hours everywhere on Earth. Changes a little bit. I think we're like 12 hours and 5 minutes is our day length tomorrow. But depending on where you're at on Earth, it's within that 12-hour mark. At the solstice, though, we are either tilted, depending on which hemisphere we're in, we're tilted towards or away from the sun. So winter solstice, for us, we're tilted away from the sun, so we have a shorter day length. Summer solstice, we have a longer day length because we're tilted towards the sun. And of course, it's the opposite because of that tilt from the northern to the southern hemisphere. So in the southern hemisphere, while we're experiencing going into autumn, they're experiencing going into spring. When we get into the higher or lower latitudes, we have almost no light in some cases. If you go to Alaska or you're in the Arctic Circle, then there is, on the winter solstice, no daylight. So as you might imagine, that's very unfavorable for the growth of plants. So what do you do? With short days and low light, you can either import everything, or you could kind of introduce artificial lighting. And of course, this isn't really practical to do outdoors, but in controlled environment agriculture, we have supplemental artificial lighting that drives photosynthesis in things like greenhouses and other indoor production facilities. So we have lights like HID or LED lights that are promoting this growth when the light intensity or duration is too low. It is pretty wild, though, to think that your cool season vegetables can grow very fast and large in the long cool days of summer in those areas of higher latitude. They produce huge cabbages in Alaska because of that. They've got a cooler season, but they also have really an intense and fast growing season there in that short period of time that has it, because in the summer they have almost 24 hours of light. So I know a lot of this is kind of common sense and you've heard it all before, but just thinking about it in terms of agriculture, it's important just to examine it again. So plants, of course, have kind of a biological clock, and they're able to keep track of the duration of light and dark. We have plants giving different responses to different periods of day length. So some will just according to day length, open buds, have leaves open, or flowers open, or have flowers or leaves fall, depending on a critical day length. But that's not all plants. That's just, we have different responses for different species. So some are totally to light. Others are also with temperature too. Most of them have some response to both. Plants that do flower in response to day length are called photoperiodic. They respond to the photoperiod itself. And the photoperiod is just the amount of light in terms of duration, the hours of daylight, and the response between light and darkness over that day. So we have plants that flower due to longer days, the long day plants, and those that flower due to short days, the short day plants. Makes sense. And again, this is also it can be modified. It's either obligate, so they have to have the certain photoperiod length in order to flower, or facultative, where it helps them to flower. They flower more. They might not have as many flowers if they don't have that right day length. So day length is important for some crops, especially talking about things like soybeans and onions. Those are two plant crops that are very sensitive to day length. And you really have to look at what your photoperiod is, what is your latitude, to know which varieties you can grow. Fortunately, breeders have come up with a bunch of different cultivated varieties that are able to respond to short and long day. So for the onion example, us kind of being at the mid-Atlantic, kind of this sort of median in latitude, in terms of photoperiod, we can actually grow either short day or long day onions and have them bulb up. But if we go much higher, then we need to look at having longer day varieties. I think it's kind of interesting to note, and it seems kind of counterintuitive that there's a lag kind of in time in terms of how the photoperiod responds to season. I mean, we're getting ready to have the equinox, but you don't see an immediate response in terms of temperature. So, after the equinox, the days are getting shorter, but it's not necessarily immediately getting cooler. It's kind of this interaction of light and climate and weather, all these factors together. And those are all very important for us to examine in trying to produce crops optimally in different places. So we look at the photoperiod and also just the intensity of light, the amount of light we're getting in terms of the just number of hours over a day, but also how intense that light is that is actually getting to the plant, depending on whether there are, say, barriers like, say trees, for instance, that are blocking the light to getting directly to a plant. That changes the way that spectrum of light is perceived by the plants. So we have both the quantity and the quality of light affecting plants, and the way that plants respond to that by their shape or their actions is called photomorphogenesis. So we usually think of that as due to stretch. Plants get leggy when they're stretching, looking for light. That's probably the most common photomorphogenesis kind of response that we see. But we also have particular plants like sunflowers, for instance, that do solar tracking. So they actually move their leaves throughout the day with the sun to absorb the maximum amount of sunlight. So plants have adapted differently to get the amount of light that they need. And that is all due to a light absorbing protein called phytochrome. And it basically governs the way that plants are able to perceive light, both in terms of quality and quantity. So what we get in terms of quality is we're looking kind of at that electromagnetic spectrum. And plants respond to, again, to that kind of red light. If we're looking kind of, it's on the longer end of the spectrum. So we have red and kind of far red, and then infrared, which is not visible, but we get a response in terms of heat from that electromagnetic radiation. Plants can actually, depending on the plant, have an effect on infrared, but the far red light, if it is higher than just your regular red light, then you get this kind of shade avoidance response where the plants are reaching for the light. So we see that a lot with greenhouse crops. If they're kind of packed together too close, then they will try to avoid shade, and so they'll grow towards the light. They'll get tall and spindly. So that's a photomorphogenic response. We also can see it in terms of just the row orientation. We want to space our crops properly, but also to make sure that the rows are going the correct way to where they're not shading other crops. And so whether you orient your rows north, south, or east, west, kind of depends on what crop you're growing, as well as if you're trying to get maybe a microclimatic response. So again, look at that per particular crop and how your row orientation can affect the light for other crops around it. Doesn't make a huge difference if you're just talking about growing just one field of just corn, because it's in a grid pattern and you're not really getting individual rows of different heights of crops. But say you were growing corn and maybe beans next to each other, then your beans usually might be, say you're growing half runners or something, shorter than your corn. So you got to plan that spacing properly and the orientation of those rows in order to reduce the effect of shading of plants. We can also see different responses in different plants using different colors of mulch. Darker mulches, for instance, are going to absorb more light. So in vegetable production, a lot of growers use black plastic early in the season to warm up the soil quicker, because it's helping to absorb that incoming light and increase the temperature. Kind of has that microclimatic effect. For some crops, though, say cool season crops, they actually might use a white plastic mulch, so it's reflecting that light instead of absorbing it. But there's also all kinds of other colors. I mean, they're doing different, kind of seeing different responses in different varieties of different crops. Like for tomatoes, some varieties have, I guess, done better under a red mulch. I'll try to put up a link for that for you guys to check out. But Pennsylvania State University's been doing a whole lot of research on these different colored mulches and how different crops respond to them. All right, so light, of course, is a main driver of temperature. And I think all of the climatic factors start with light, but the other big thing is moisture. So moisture, of course, we have to have it for plants to grow. Most of our plant products are 90% or more water. They use a lot of water to grow. So it's important to look at the fact that most of the world's water is salt water in our oceans. So almost 98%. The remaining 2% is, or much of the remaining 2% is frozen, not all of it, in glaciers. So our actual fresh water, our groundwater, and whether it's in creeks, lakes, or streams, exists as a very small fraction of it. 0.01% is fresh water. And then another very small part of it that is very important, though, is just in the atmosphere as vapor. So we look at both groundwater and surface freshwater supply as fluctuating and eventually being replenished through the hydrologic cycle, which is also driven by that input of solar energy. And of course, it is a global cycle. So we see this happening around the planet, and water is just like matter in that it cannot be created or destroyed. It can only be moved. So we have water in the oceans, where other large bodies of water evaporating, condensing in the clouds, and then turning into precipitation, falling on land. And then when it hits land, it either is absorbed and infiltrated, and then recharges kind of the water table itself, or it runs off. And that could be into another body of water. It could be through a creek or stream. Eventually, it will go back into a larger body of water, which all water eventually flows into the ocean at some point. So for us, of course, the Atlantic Ocean. Well, for you guys, the Atlantic Ocean. For us, actually, it's going into the Gulf of Mexico, which is still part of the Atlantic Ocean, but nonetheless, a little bit different pathway there, depending on what side of the continental divide you're on. And for us in the mountains, we're going into the Tennessee River watershed, whereas I guess you guys are going into the Chesapeake Bay watershed. So important to look at the watersheds, how much water is available, and looking at these whole watersheds, I think, is very important to try to slow runoff of water down, try to infiltrate more water. It's probably the best place we can store water is really in the soil. So we're affected, the hydrologic cycle affects our ability to produce crops, and our crop production affects the hydrologic cycle as well. So when we're looking at available moisture, we look at it in terms of either through precipitation, or what water is stored in the soil, what water is stored in the plant itself, as well as what we can bring in from other sources. But we have to look at that availability kind of on the time scale. We need that water to be most available when the plants need it the most. And it moves through the plant constantly. So we have evaporation from the surface of leaves, as water condenses, moisture falls as precipitation. We see that happen pretty quickly. Right after a rain, you see all that water vapor, clouds rising. That's evaporation taking place. But we have evaporation plus transpiration, which is that water just moving through the plant and out of the plant. So we combine those two, evaporation and transpiration, to be evapotranspiration, the sum of evaporation from the earth as well as transpiration from plants. And that's what is really driving that hydrologic cycle affected by the solar radiation. So water moves from soil through the roots of the plant, through the stem, and out of the stomata, the little pores on the undersides of the leaves. And in doing that, it's cooling the plant down. It's their version of sweating. But it's also helping the plant to breathe, to respire. As they're transpiring, they're also respiring, moving energy. And for plants to actually photosynthesize, they have to be releasing that water through those pores on the undersides of the leaves. So again, if we want optimal crop growth, we want to maximize photosynthesis, and therefore we have to also maximize transpiration. Some plants transpire so much that they look like they're always wilting. Like if you look at a squash leaf, for instance, in the middle of the summer, if that temperature is high enough, humidity is so high that the air can't take much more water vapor from the plant, and you start to see those leaves wilt because they are transpiring so much. They can't bring in enough water to make up for that transpiration. So we have water in the air as well, and that amount of water vapor the air can absorb depends on what the temperature of it is. So in the summer, of course, it feels very humid because warmer air holds more water, and therefore we get more moisture, we get humidity rising. Cooler air holds less water, so we tend to get, in our area, actually more precipitation in the winter because it can't hold as much moisture. It's falling, it's condensing. As moisture-laden air moves to cooler or warmer regions, then we have condensation happening, eventually forming clouds and causing precipitation. And then when that precipitation hits the ground, it either penetrates the pores in the soil and infiltrates, or it runs off. And that's going to be determined by the actual properties of the soil, as well as the topography of the land, how much water is already in the soil. More on that later. But ideally, we want to try to prevent runoff on the farm scale. We want to try to absorb as much moisture as possible. And plants help to prevent runoff and help to encourage infiltration by basically just slowing that water down, capturing precipitation on the surface of the plant, channeling it into the roots. So very important. If we want to try to prevent runoff, then we want to keep something in place, usually plants growing in the ground. So runoff, of course, is a big deal because it's moving. It eventually will find its way into some body of water, whether that's a stream, river, lake. That water that infiltrates eventually is going to end up in groundwater. It recharges that water table, which is very important for us because it's recharging the aquifers, these natural underground reservoirs that become very important for us to pump water out of so that we can irrigate. So we're looking at the relationship, though, between precipitation and evaporation as a major factor in determining the climate of a region and its suitability for plant or crop growth. The ecosystems are often determined by the amount of precipitation that they have. So I talked about deserts as being one of the largest biomes. Lots of land mass that, because those trade winds are taking bodies of moisture away from them, they are not able to support as much natural plant growth, or the plants that are there are much less. So the whole productivity of that ecosystem is lower, even though it's a large mass of land. Whereas on the opposite end, we actually say rainforest is just defined purely by the amount of precipitation it has. So we get over like 90 inches of rain and you call it rainforest, whether it's in a temperate or tropical climate. We got to look at moisture availability in terms of determining the needs and ability to grow crops. And we have to look at our crops in terms of their seasonal needs and their day-to-day water needs, as well as this relationship between our water supply and the demands of the plant. So in this graph, just looking at corn in its different growth stages, as it's vegetative and it's getting taller, it needs more water to maintain that plant. And then as it shifts into its kind of sexual reproduction, as it starts to produce male and female flowers, then it needs even more water until it kind of levels off, and then it starts to kind of utilize that water. And then as the plant moves into producing seed, initially it needs this kind of the same amount of water, but eventually it starts to level off and drop off as it's utilizing all of the resources it has into producing a finished fruit. And for corn, we want it to be dry at the end, so we want there to be lower moisture kind of later in the season. So there's a whole lot of factors to consider when it comes to, how much water do we need to apply to a crop, or how do we make sure the crop is producing optimally. So we look at the water in terms of what is in the ground as well as what is in the air, and water in the air we look at in terms of humidity. Relative humidity is something that is a figure that we look at a lot. It's the actual moisture in the air versus the amount that air can hold. So humidity is very important for holding moisture, for kind of allowing transpiration, but it's not the best figure when we're talking about trying to determine necessarily how much water we need to apply. So it is important to look at the dew point, because dew point is when relative humidity is 100%, and that moisture basically is either condensing on the surface of a plant or turning into rainfall. So if the relative humidity itself is less than 100%, then we look at the difference between the actual vapor pressure and the actual humidity, the actual amount of moisture in the air, and the amount of air or water that the air can hold. And the difference between those is this VPD, the vapor pressure deficit. And vapor pressure deficit is a figure that we look at more for, determining how much water is lost through a plant. So just in this graph, we're just looking at that effect of temperature change on the VPD at the same relative humidity. So at a higher temperature, vapor pressure deficit is much greater. Therefore, water loss would also be greater. And just looking at the humidity is not going to indicate that, but the VPD will. That's very important in greenhouses and controlled environment agriculture as well. Humidity can have positive and negative effects on plants, and depending on what kind of stage that they're growing. So generally, what we think of in terms of water over the season, we want there to be enough moisture for spring planting in the soil so that we can work the soil, so that we can get plants started. But it's also important to note that we have too much water, then it can prevent seeds from germinating, it can smother them, it can cause rot. So we need the Goldilocks amount of water, right? We need just the right amount. Too much makes things worse. Too little, you can't grow a dang thing. So what we were looking at is trying to figure out successful water management. So we're going to try to regulate the availability of water to meet evaporative demand. And we're going to look at that in terms of the amount of precipitation that we have, which needs to be either equal to or greater than what the plant is transpiring in order to keep photosynthesis going. So if our precipitation patterns don't match our water needs, then at some point in the cycle, we need to move to irrigation. And I think that's a good stopping point. So we started a minute early. We'll also end a minute early. Anybody have any questions or comments?
Yes, sir.
All right, well, I'll get the quiz up for this chapter up today, but we'll finish off discussing this chapter on Wednesday. Y'all have a great day. Good luck on your test.
Okay, you have a good one too.